Hello and welcome. Thank you so much for taking the time out of your day to meet with me and talk about realizing AI at the edge. First of all, I'll tell you a little bit about who I am so you've got an idea of who's talking to you and why or why not you should maybe listen. I always think that's an important, anytime you look at new information, you want to understand who's giving that information to you and whether you should take it on board or not. So I've been in the electronic industry now, probably getting on for 25 years. I've worked across a multitude of different parts of the industry. I've been a chip designer, worked in software, you need to put your headphones on, ma'am, if you want to hear me. It's on the back of your chair. Worked in hardware, worked in software for different sizes companies too. So I've worked at small startups, worked for quite large multinationals, and I've also been an independent contractor. So I've got a reasonable breadth of the electronic industry and what I've done in it. Oh, and for those of you, they normally say put your phones away, but if you want to, you can scan this QR code and that'll give you my contact details on LinkedIn. I'll show it again later. So today we're going to have a quick look at really, what is AI and why to use it, why we should use it at the edge, the 5 steps that I consider when taking an AI model and bringing it to the edge, and then I'll very briefly touch on what Arrow can offer you to help make that journey a little bit smoother. So AI is a lot of different things to a lot of different people. But today, really, what I'm interested in is deep learning. So I'm sure all of you have probably seen this graph before, but just to very, very quickly summarize it. So AI is the huge topic of anything that a machine can do, doesn't have to be a computer, anything that a machine can do that mimics something that a human could do. That could be a really simple decision tree or something slightly more complex. Moving then a little bit closer to what we're talking about today, we have machine learning. And that's instead of us as a human having to create an algorithm to describe this behavior, instead the machine learns. And then finally, we're talking about deep learning, and that's where we use multiple layers of network to enable the AI that we're going to be using. Okay, so why use AI? Now, hopefully the answer to this isn't because the director of product marketing said, our products are really good, but they have to have AI in them tomorrow. Hopefully you actually have a reason behind it. And there's lots of complexity around why you might use AI. I try and think about it quite simplistically. I think we can all agree that that's a 4, as is that and that. They're all 4s, but they all look different. Okay? Just like we can read all of these numbers. Any child could read all of these numbers very simplistically. But what I'd ask you to do for a moment, imagine you're a design engineer and you have to write a piece of software. Sorry, I'm speaking really loud because it's loud around here, but am I too loud in your ears or is it okay? Okay, so imagine you're a software engineer and you've got to design something that will read those numbers. It's a really, really non-trivial task. To think of what you would have to do, you're going to have to, first of all, have some sort of like contrast awareness to work out the light and the dark, so you know what pixel's an active pixel and what one's dead. Then you're maybe doing things like, looking for lines, looking for curves. But then how would you handle the fact that there's like 3 different types of 4s? And those are just the ones that I drew, let alone the ones that other people might draw. So as a design engineer, the really simple task of just reading numbers is actually really hard to do. And it would take an immense amount of effort for somebody to program that. And historically we did, right? We used things like, cosine Fourier transforms and all sorts of other very clever image processing techniques to try and do this. And so why AI? The idea of AI is that we replace the ingenuity and time of a design engineer with lots and lots of compute resource and lots of data. So instead of having a design engineer spending time working out how to describe this algorithm, we just use lots and lots of computers and lots of data, and we let them work out how to do it themselves. That's really the only reason you should be using AI. When your problem is really too complex for a human to come up with a simple algorithm, and instead you let the computer come up with the algorithm instead. Okay, when we're talking about AI, there's kind of two main things we need to understand. Training and inference, especially if we want to talk about edge AI. So training is the process of learning. And what we've got here, you can see. Okay, oh, it does work, but it's really, really dull. I'll just point instead. So what we've got here is lots of data. So it could be like thousands and thousands of examples of handwritten data. And we feed it through our neural network. And we then look and see what our network thinks the answer is. So we put in a 4. It thinks it's a 7. That's an error. And then using mathematical regression, we basically feed back the fact that it's wrong back through the machine, and that updates all the different weights and activation functions so that the next time it gets slightly better. If any of you were RF designers, you might remember designing like bandpass filters where you'd maybe have like 10 or 12 coefficients. You could play with MATLAB. You can move your coefficients up and down until you were cutting out just the bandpath that you wanted. AI is really just lots and lots and lots of very simple maths, but it's lots of it. So instead of having 10 or 12 coefficients, instead of coefficients, we call them weights. And instead of having 10 or 12, we maybe have millions. And so as a human, we just can't tune all those figures. And that's why we allow the machine to do it itself. And so this training, it normally happens in data centers, right? Using vast amounts of data, vast amount of compute resource. But where I get excited about AI is where we get to here, which is the inference. That's when we take that trained model, deploy it into something that's useful, and then all the inference does is look at a new piece of data it hasn't seen before, and it predicts what the answer is. And I guess that's the other key thing about AI. It has a percentage confidence about its output. And that percentage confidence will vary depending on what level of certainty you need, but it's probably never going to be 100%. Just like if you look at a number and it's badly enough written, you may think it's a 6, but it's a 9. You know, just like we're not 100% accurate, this will not be either. It's all based on statistics. So this is a slightly modified version of what you might have already seen. I've kind of redrawn this to be more like engineering rather than AI based. Just using the same symbols that you would see in any electronic circuit. You know, we have an input. The input is multiplied by some weight. All the inputs and all the weights, including your bias, are added together. And we then have an activation function. All an activation function is it looks at the number that's been added together and says, is that good or bad? You know, am I going to turn on, or am I saying this isn't it? Now, lots of different activation functions. Up in the corner here, I've just drawn one of them, which is a rectified linear. So basically, if a number is too low, the output's 0. Otherwise, the output is linear with the input. So that's really all it is. AI is that simple. It's just adding and multiplying. So most people, when they think about AI, they often think about Big Brother. They think about Chat GPT and various other AI that's implemented in cloud computing. Why is there so much interest today in bringing it to the edge? So I've highlighted here some of the key areas. First of all, ultra low latency. That's not just the time taken to gather the data, send it up to the cloud, get the answer from the cloud, and then put it back down to the device. It's also latency based around things that need to happen in real time. If you're driving a car and you want it to brake by itself, ideally you don't want it to have a little chat to something in a cloud first. So that's an obvious example, but there's lots of other times where you want really low latency. And that could be even on very small, simple microcontrollers where you're perhaps tuning your noise cancelling headphones. Now, noise cancelling headphones, they don't work using AI traditionally. They work using a very simple, you look at the waveform coming in, you negate it through a filter, add the two together, and it reduces the noise. Where the AI comes into that is it works out what environment you're in to change the filters that you might use inside your headphone. So first reason to have it at the edge, super low latency. Reason number 2, resilient. If you're talking to your Alexa or your Google at home and you say, Alexa, the only bit that's happening at the edge is the word Alexa. So your Echo has enough AI in it to recognize the word Alexa. If your internet was down and you said, Alexa, turn on the lights, it would recognize its name, it would turn on, it would realize that there was no internet, and it would therefore say, sorry, I can't connect to the internet, try again later. Your lights wouldn't be turned on. And so by having the whole algorithm, the whole model at the edge, you get rid of that. You become more resilient. You're not interested in having connectivity. Enhanced privacy and security. If everything's being processed where you are, then none of that data is being transmitted. So because of GDPR and various other concerns, say, for example, I wanted to know how many people were here, and I had a camera that was like recognizing faces, all that I would get out of that camera is a number. And so the only data I'm collecting on you would be the number 50, the number of people sitting down in the auditorium. I'm not taking all of your faces, sending it to a cloud in a country where we might not know which country it's in, and infringing your personal rights. So privacy and security, if you're not transmitting something, it can't be intercepted. If it can't be intercepted, it can't be seen. And if you're not relying on external data, you're generally more secure. Comes down to reduced data transmission, and actually reduced data transmission and reduced power I'll speak to at the same time. So if you think about a generic device that has some sort of AI and it also has a radio, and by radio, I mean that could be Bluetooth, it could be Wi-Fi. I'm not necessarily talking about your traditional AM radio, but you've got a transmitter in there. Roughly, on most designs, 70 to 80% of the power used by that design is by its radio. And so if you can reduce the amount of time you have to transmit, then your device will last longer. And so perhaps you've got like a monitor out in a jungle looking for poachers. Then that model can come on, it can say, there's movement. That's step 1 of the model. Then it can fire up another core and say, that movement's human. And then it can fire up an even better model that says, and they look like a poacher. All of that's happened without radio transmission. At that point, you then radio back to base and say, I'm device number 4, I'm at location XYZ, and I think there's a poacher. And that's the only bit you're transmitting. That can live out in the wild for years on a small battery. If it was relying on the cloud to do all that modeling, then it would be dead and have to be replaced every day. Another point of data transmission is the cost of data transmission. So it's not just the power consumption, but it's also the actual cost of having data. If you've got a SIM, if you're broadcasting it via mobile, there's a cost associated with that within your product. One final thing on power. Sometimes when I talk to people about power, they're like, well, power doesn't really bother us because we're designing quite a big thing and it's going to plug into the wall. So we don't need it to be battery operated. If you can reduce the amount of power your device uses day to day, then you can reduce the size of the power regulators. You can reduce the size of the capacitors. You can reduce the amount of thermal cooling it needs. Maybe instead of having a fan, it's totally passive. So just because you're not power limited, always think in terms of saving power. Not just good for the environment, but it also significantly reduces your BOM cost of your final product. Okay. Let me just check how I'm doing for time because I know I can waffle. Not too bad. So AI is more complicated than 5 steps, but I'm going to talk to you about it in 5 steps because I think it kind of captures most of what it is you have to do. And obviously, depending on whether you're a data scientist or an embedded software engineer or a hardware engineer, it will depend on which one of these steps you think, oh, I feel comfortable with that step. I don't like the others. And generally what we see is we tend to work with a group of customers who are 100% AI experts, know more about it than we do. They're maybe not so familiar with embedded software and embedded hardware. And then we also work with traditional customers that know all about embedded software and embedded hardware, tasked with putting AI into their product, not sure where to begin. So stage 1, data engineering. Often, and this often surprises people that are used to designing hardware, data engineering is often the most expensive and hardest step in your journey. Getting access to data, I mean, a lot of data is publicly available, but getting access to good quality data, analyzing it, changing it, configuring it. A huge field at the moment, synthetic data, where you generate data for scenarios that you can't capture live. You say you're designing a robot to work inside a factory. You don't actually want someone to cut their arm off so that your AI knows to recognize that somebody's had their arm cut off and send an alarm. It's much better to do that synthetically. Once you have that data, and like I said, it's a huge step, you then train your model. And typically, this step here, this is what your data scientists do. However, we do have fantastic software out there now. Amir from Edge Impulse is talking over on that stand. I think about 4:00 today. He'll tell you about Edge Impulse. It's fantastic. You also have Neutron AI. A lot of other vendors have got really good software tools. Infineon have got Imagimob that help embedded engineers go from the data engineering right the way through. But let's assume we're doing it the hard way. So you've completed your data engineering. You then go on and train your model. That goes back to the providing vast amounts of data to really, really large cloud computing resource to end up with a trained model. Now, these trained models, they're normally trained in floating point 32. They're normally really large. Like I said, they can have millions and millions of parameters. Far too large for us to use on the edge in a nice, efficient way. So that's where we go to model optimization. Model optimization, primarily 2 or 3 techniques. We have quantization, pruning, and possibly transforming. Once you then have your smaller model, you then have to choose a hardware platform to deploy it on. And that's a whole area in itself that we can talk more about at a later time. But basically, it can be anything from the simplest microcontroller right the way through to specifically designed system on chips with AI accelerators and pipelines. Normally, at this point, I'm quite happy to say, job done, shake everybody's hands and walk away. However, you do then have to monitor, once you've deployed your AI model into the field, is it working as you would expect? Things change. The environment can change. Your model can be unintentionally biased. There's a great example where an underground company that's not too far from here was training an AI model to recognize whether underground platforms were busy or not. They fed it lots of data in the lab. It was getting 98 to 99% accuracy. They deployed it in the field. It didn't work at all. That's when they realized that all the data they had fed it, when the platforms were busy, it was rush hour. And when the platforms weren't busy, it was the middle of the day. So what they did was they spent an incredibly large amount of time teaching an AI model how to read an analog clock. So if the model saw it was 9 o'clock, it said it was busy. It didn't care if it was 9 o'clock in the morning or 9 o'clock at night. It reported the platform was full, even if it was empty. So you do have to be careful, and you do need to monitor the results you get. So then looking at some of these steps in just a little bit more detail. So the data engineering, as you can see, vast numbers of different sources you can get it. Today, really what's very much recommended is try and find a model that already does what you want and just feed it the additional data you need to train it to do your precise requirements. So don't start with an empty model. One of the things I kind of just want to highlight here is that when you're doing your gathering, there's vast amounts of public data sets available that you can use. They may not be exactly what you need, but a lot of the features that your model will learn from those, it will train it so whenever you're giving it your exact needs, it's already halfway there. Just very quickly mentioning then the difference between closed and open problems. An open problems where you're not in control of the environment, anything could happen. Closed problem, generally the environment's much more controlled, your model can be much simpler. I'm sorry, these slides are going to be available afterwards. I have to be a little bit careful on the time there, so I'm not going to go through all the slides in detail. Instead, what I'll do is I'll just pull out a few points. So I already mentioned synthetic data. So that's like using like a simulator to create the data. But some of the other things you can do is deliberately introduce noise, flip your images and play around with them. So once you've collected your data set, there's a lot you can do to help your data set be more diverse without actually having to go and collect more data. And then one which often catches people out, deduplication. If you're gathering data from lots of different places and some of that data has the same images, then what happens is that your model becomes overly tuned to what it sees most frequently. So if I was training a AI algorithm to recognize a dog, and I used all the photos that I have of dogs, that algorithm would be really, really good at recognizing English Cocker Spaniels. May not be so good at recognizing everything else, because most of the pictures I have are of my dog, not of someone else's. I know that sounds obvious, but when you're getting your data from lots of different places, do be careful of unintentional bias because you're using the same image more than once. Okay, when you're doing your training, I already mentioned it, do what's called a state-of-art research. Have a look at what models already exist. Try and get one that's close. When you find one that's close, that becomes your baseline. And then what we do is transfer learning to make that model do what you need to do it. So if you think of a model as having, say, 10 layers, the input layer is the most generic, and the output layer is the most specific. So if you unlock the output layer and maybe layer 9 and layer 8 so they can change, but say to your rest of your model you're not allowed to change, and run new data through it, all you're doing is tuning the specificity, I can't even say that word, sorry, of the model, and the rest of it stays locked as it was. An excellent tool for doing transfer learning, and it's brilliant because it's now open, so you can use it for multiple different factors, is NVIDIA Tau. It used to be if you used NVIDIA Tau, you were in the NVIDIA ecosystem. Now you can use NVIDIA Tau. Try your model on a Jetson, and if the Jetson's far too powerful for what you're trying to do, you can then take the same model and try it on other devices. You can try it on NXP, on ST, on Infineon. You can try it on FPGAs. So the fact that NVIDIA have opened up their Tau toolkit, it means that all of a sudden there's this massive ecosystem of people that know NVIDIA that can now work on all the other devices as well. So that's a slide just on transfer learning. Well, we've kind of already covered that. So model optimization, I think most of you kind of capture this already. You know what quantization is, you're all engineers. But basically pruning, when you have, if you're multiplying something by a number that's close to 0, you just set it to 0 and remove that whole piece of mathematics out of your model. Or if the output going into another input is often 0, again, you can just remove that connection for that particular one. What we've discovered, has been quite surprising, is we used to try and train models with limited resources, thinking that would produce the most effective models. What we've discovered is if you train it with almost unlimited resources and then aggressively prune it, you actually end up with smaller, better performing models than if you started your training aiming for the embedded place. Okay, this is ridiculously complicated to explain, but I'll do my best. Normally, when you're training a model, you have data and you've got labels. So, is it a dog? Yes or no, and what percentage? So you train a teacher model, a big complex model, and it has all the answers. Now, when you're training the student, the bit that's different is when the teacher model has an output, it doesn't just say it's a dog. It says, I'm 80% sure it's a dog. However, 10% it might be a cat, 5% it might be a drawing, and 5% I don't know what it is. And so instead of getting your student model to try and aim towards 100%, which is how you train, you get it to aim to be as good as the teacher. So that's in a very simple way the concept behind knowledge distillation. You're not only providing the input and the output as the answer, you're providing the percentage answers as well. And that allows the student model to be smaller and more general. Okay. So how do you choose what device you're going to put your model on? So often people look at these numbers first, the GOPS and the TOPS, giga or tera operations per second. Again, AI is just mathematics, so you just count the number of mathematical equations your device can do that gives you that answer. And that's a great starting point, right? If you understand roughly how many GOPS or TOPS you need, then you're going to be in the right ballpark. But then you need to look at two factors which are normally the opposite of each other, throughput and latency. You can think of throughput as the number of things you get from the start to the finish, and latency is the time it takes from the first thing to get from the start to the finish. So if you look at, say, like a ferry going from the UK to France, think of all the time it takes to load those cars on, but then you have a ferry journey and they all come off. So the time between the first car arriving to the first car leaving is quite long, but when that first car leaves, 500 cars leave with it. That's your throughput. Latency is much more like driving down a little country lane where you can maybe only do 60 mile an hour, but it's just you, and you still get there faster than if you had to like wait and queue to get a big group of people together. Some problems need throughput, some need latency. If yours needs both, then good luck. Power we've already mentioned, right? You know, designing for low power isn't just because you don't have mains, it's because it makes your entire BOM and your entire system cheaper and simpler and more robust. And then cost. At the end of the day, we're trying to design an AI system that's good enough for what you need, not one that's perfect. And there are lots and lots of ways to go from really high-end chipsets down to microprocessors, down to microcontrollers. And I'll cover that. Whoop. Come back. Okay, I've just given you the answer to the next bit. So here we have a microcontroller, maybe like a Cortex M33, something like that. Nice, simple 32-bit microcontroller, more than capable of running tiny ML models very efficiently. If you then add a neural processing core into that, then two things happen which are a little bit surprising. First one isn't. It obviously performs much better. But the thing to me that's surprising is it uses less power. And that happens for two reasons. One, neural processing units are really, really efficient at the maths they have to do. And because it's specifically designed hardware, it does that mathematically more efficiently than using the general mathematical block in your MCU. However, because it also does the inference faster, even if it was drawing more power, it's drawing that more power for less time. Therefore, your total energy budget comes down. And roughly, a microcontroller with a neural processing unit is about the same level of AI performance as a microprocessor. Now, obviously, if you're running Linux or something, then you need your microprocessor, because all I'm talking about here is the AI performance. Now, if you do need to run Linux and you do need to run AI as well, then there's a great range now of microprocessors also with neural processing units in it, and they achieve the same sort of results. Higher performance, lower power use. And again, it's the lower power use I think people find surprising. They normally think, hey, if I'm using a microcontroller and I'm on the edge of my power budget, I can't buy a bigger microcontroller that has an MPU in it, or my power budget will be totally blown. But it actually uses less power. And I think that's a real key takeaway, because a lot of people are surprised by that. Now, the first thing in this slide I have to point out is that it's illustrative and not to scale. Okay, all I'm trying to do here is give you a feeling of what is out there as far as devices that you can get for AI. Okay. ST actually makes sensors with small ML cores on them. So if you can't get any closer to the edge than on the sensor itself. Very simple ML cores may be enough to do some of the processing you need. Then at this level here, we're basically looking at the microcontrollers. Then the microcontrollers with a MPU in them. Microprocessors with MPUs. So this is the Qualcomm Snapdragon, the NVIDIA Jetson. You're probably familiar with both of those. Very high AI performance. Something we haven't touched on in this talk, but I'm happy to talk to you about it at another time, is the performance that you can get out of FPGAs. So here we've got a Lattice, a Microchip, and Altera FPGAs for doing AI as well. 1 minute. Okay. Okay. Like I said, normally at this stage, I consider myself finished. I'm nearly out of time, but I will mention the fact that we're not finished. So once we've done a model, we do need to check it and continually optimize it. There's so much that can go wrong once you deploy it into the real world. Okay. Arrow have a range of services to help you. You can get the slide deck, so I'm not going to go through this with the limited time we have left. But let me just say that regardless of what stage you are in your journey, we can help you with that stage, whether it's a full design service or just a little bit of guidance over what chip to select. Here are some final thoughts to take away. First of all, if you're interested in AI, have a go. It's incredibly simple to do it. You don't need any tools. Loads of people have free software. Have a play. It's not on the slide. This book's written by two clever people at Edge Impulse. Their software is great for having a play and understanding how AI works. Use transfer learning. Start off with models that can already do what you need. If you're an embedded engineer, try and use an end-to-end software suite. If you've got your own specialists, different story. Last point, I haven't really touched on it, systems on modules. If you're moving from, say, people that design with microcontrollers to using microprocessors with Linux and AI, that's a big jump. You can buy modules to help you do that. And it might be a good place to start, especially if the processor isn't a key part of your product. I'm running an AI webinar series. If you grab this QR code, you can see it. 2 o'clock European time every Monday. You can also access the back catalog. Just give me a nod when you've all seen that, because I need to show the final slide. Oh, sorry. We all good? Okay, I see all the phones down. And then finally, if you're claiming CPD credits for this talk, that's the QR code that does that for you. Thank you all so much. I am a little bit over, so apologies. Thank you for letting me finish.
Thank you.
Thank you.